we have a new homework assignment. It's about factors, okay? But the whole point is to make use of structures, okay? Which is something that we talked about last time. So it's about structures, it's about pointers, okay? So both of those things we talked about on Monday. I'll go over the homework assignment today, okay? Just briefly go over what you need to do, and then I'll see if you guys have any questions about it. And go ahead. The internet is up now. Pretty good. Yep. Okay, so the new homework assignment is under structures, okay, and it's called fraction math. Okay, I'm hoping that some of you still remember how to simplify a fraction. Like 32 over 8 is 4 over 1. 27 over 30 is 9 over 10. That sort of thing. Okay, so I want you to write a subroutine to do all that. Okay, and I'll give you a structure that will basically be used to represent fractions. So this is the homework assignment. It's called fraction math. And in some way, it is related to find factor, okay? Because factoring definitely has something to do with simplifying a fraction. So in this case, I want you to create 2 files instead of just 1. So the first file that you need to create inside the folder called simplify is fraction.h. It is called a header file and therefore an extension of .h. It is a convention. This is the content of the .h file, and for the most part, you just copy and paste it, okay, or just type it into. Oh, this part is not supposed to be here, so let me fix it first before I forget, because I tend to forget. Okay, so let's fix that. It's there. Okay. It has to do with this part here. And it's because of this one here. So let's do LT semicolon, GT semicolon. It has to do with HTML does not represent less than or greater than by itself. You need to encode it in a certain way. All right, so now it is all fixed up. Okay, this is the way you just type it in, but you have to save it into fraction.h, as a file. It doesn't really do much. Okay, the first thing it does is I will explain the if, pound, if, ndef, and pound define later on. So for the time being, all you have to do is to type the program as it is. The most important part that does relate to this class is this part here. I'm defining a structure, and I give it a name, and it is called fraction with an uppercase F. This is a cookie cutter, okay? This is the name of a cookie cutter. It is called fraction. So you can use this cookie cutter to create actual cookies so that you can use those things, in your program. Inside this particular structure, there are 2 components. And by the way, the components of a structure, each one is called a member, okay? So in this case, we have 2 members. The first member is called numerator, and the second member is called denominator. Okay, so those are the 2 components that you need in order to store a fraction. We are not dealing with 1.5 or something like that. So 1.5 is going to be represented as 3 over 2, which has 3 in the numerator and 2 in the denominator. Are there any questions about how this structure is going to be used to store a fraction, to represent a fraction? Yep.
I don't understand how to make it 2-folder. I don't understand it. 2-folder.
1 folder, 2 files. There's only 1 folder, which is simplify, and this particular file is named fraction.h. Okay, that's what the instruction says, right? Okay, put the following content into a header file, not folder, named fraction.h. Is that okay? and you're supposed to do everything inside a simplified folder. Okay? All right, so this will define the structure, which is a cookie cutter. And with this cookie cutter, I want you to define 3 functions, 3 subroutines. The first one is going to be this function. And the way I describe it is I describe the return type, which is void in this case. The name of the function is fraction simplify. And the parameter is pf as a pointer to a struct fraction. Okay, this is what we call the prototype of a function. Okay, it describes the return type, which in this case is a void. It doesn't actually return anything because it is going to do everything it needs to do to the actual thing, to the actual fraction, which is pointed to by pf. So the description is this part. This is a subroutine, which is also known as a function in C and C++, to simplify the fraction pointed to by the parameter pf in this case. For example, if it is representing 32/8, then you have to simplify that to 4/1. If it is representing 27/30, then you have to simplify it to 9/10. Okay? Are there any questions about what this subroutine or what this function is supposed to do?
Do you actually want us to use the parameter pf, or is that applicable?
It is a parameter pf, and you can name the parameter to something else, but that's the only thing you start with. This is the only information you get when you're in the subroutine. Now within a subroutine, you can define local variables. You can use any control structure that we have talked about so far. So it's entirely up to you what you want to do inside the subroutine. But from the outside, this is how we see the subroutine. Okay, it has a return type of void, which means it does not actually return anything. You cannot put the invocation where you're expecting a value. It has one parameter, which is pf, and the type of the parameter is a pointer to a struct fraction. Do we have any questions about this? Have we seen anything like this before? Okay, turn the clock back 48 hours. Okay, we talked about something about the same. Okay, so let's go ahead and look at all 3 functions first, and then we'll kind of go back to what we talked about on Monday and see how it is related. The second function I want you to implement is fraction scan. Okay, which in the previous class we call it scan date. Okay, it's about the same thing. We want to read from the standard input file using scanf a fraction. The format of a fraction is number/number, which means the numerator / the denominator. Okay, the usual way people represent a fraction. And I want you to store that fraction into the fraction structure pointed to by pf. So once again, pf is the name of a parameter. Note that each number should be an unsigned number, because in this case we have unsigned numbers in the structure itself. So when you're reading it from standard input file, you have to use the format string not to read a signed number, which is %d. You have to use %u to read in unsigned numbers. Like readnum in the previous homework assignment, this function should also check for errors and recover from errors. So you can use the same strategy to deal with checking for errors and also recovering from errors. Are we doing okay so far with this one? Okay, do we know how to read something that is formatted like this with a slash between 2 numbers? We have done something more complicated already on Monday. So on Monday we had something that read in 3 numbers separated by slashes because we were reading in a date. Remember that? Nah, no recollection of Monday. Okay. All right, and then the last one is fraction print, which is just printing the fraction that is pointed to by pf. So this time I wanted to print out just the same way. Okay, numerator divided by denominator. Do not include any line feed or any space within the fraction, because I would use a script to check the output, and it has to be exactly just this. Base 10 number for the numerator / base 10 number for the denominator, and nothing else. Okay. Are there any questions about these three subroutines? At least what they're supposed to do. Okay. No questions about this? Okay. So the rest of your program, which I want you to put into main.cpp, is like this. Okay, so you will put your code here. We'll do a pound include over here, and oh, you know what? I forget something. You will have to put in your own pound include stdio.h, okay, because you will be using scanf and printf. So within your code, okay, you have to say pound include bracket, angle brackets, stdio.h, otherwise the compiler will complain about it. Okay, it will not let you go without doing that. So the main part of this particular program is simple. All it's going to do is it will use the fraction scan to read in a fraction and store that into the local variable f. And then it will do the simplification by calling fraction simplified. And once again, it will do it within the fraction itself, f, which is our local variable. And then it will print it out, the simplified version. And that's it. That's your entire program. It reads a fraction in the format of a number slash another number. It simplifies it if it can be simplified. Sometimes it may not be able to simplify. If I give you 7/13, cannot be simplified. So you would just print out 7/13 as a result. Calculator?
Same idea.
Same idea as
As a calculator.
It doesn't really do any calculation yet. I thought about it. I wanted to actually do addition, subtraction, multiplication, and stuff like that. And then I thought about it again and go like, well, maybe we'll just kind of focus on simplification this time, and then we'll save addition and subtraction to the next one.
Okay.
So right now it doesn't do any calculation. Okay, if I give you 42/40, okay, you give me 21/20 because they can be simplified. Is that okay? All right. So are there any questions about this particular homework assignment other than, how do I get this started? Yep.
What should we do if it's given like not a number or something incorrect?
Okay, I will not give you anything that has a /0. Okay, that's the only condition that I'm guaranteed not to give you. Okay, so I'm not going to give you a invalid fraction where both the numerator and the denominator are both numbers, but the fraction itself is not a number. Okay, I can give you something like a/b. If I give you a/b, then you have to prompt again and say, I don't understand this. Okay, ask me again. Because that's part of the error checking portion, okay? Error checking and error recovery, which is the same strategy as in your previous homework assignment. Okay, so talking about the previous homework assignment, I give you authorization to use my code. So you can actually copy and paste my code and copy the main strategy of dealing with detecting errors and also recovering from errors from the program that I wrote, okay, from the read num subroutine that I wrote. So you can start with that one if you want to. Okay. All right, so let's go ahead and take a look at how do we get started with this program. The first one is to see if there's any resemblance to the video that we captured on Monday. Okay, so we'll go to the video on Monday, and that would be the 16th, I think. Yep. And see if we can find something here that might be helpful to us, right? Okay. All right. So we have something down here. It was kind of toward the end of the discussion that we had something. There we go. Stop. There we go. All right. Okay, so when you look at scan date, it gives you an idea of how to use a parameter that is a pointer to a structure. So you pretty much have to do about the same thing. Okay. Are there any questions about this one?
Not quite there yet. Didn't we have to get the address of a dereference pointer?
I think this one, oh, right, because this one is not quite the correct one, so we'll fast forward to the one that is fixed. There we go. Okay. All right, so I'm going to give you another sample program, just to illustrate what you need to do, with this particular homework assignment. All right, so let's get out of this YouTube here, and we'll go ahead and take a look at another sample program. So let's take a look at. I don't want to give you fractions, so I'm going to give you something else. Check date. Okay. I'm thinking about what would be a good example, and not really to review too much of your actual homework assignment. I know. Okay. Fraction dot. Okay, so this is what you need to do. Just do this part here. Okay, it's called fraction dot h underscore h in this case. Define fraction underscore h struct fraction and count and if. So this part is really the same thing as what we have already in the code, sort of. So we'll put an include std_int.h here, and then we'll define those things as uint, which is unsigned integer, underscore 32, which means they're 32-bit unsigned integers, which means each one, numerator and denominator, can only be used to represent natural numbers, cannot represent negative values. Are there any questions about this part? Okay. Yep.
Do you need underscore t after 32?
Oh yeah, yep, you're right. There we go. Okay, because otherwise the type name does not match. Okay, so this is what we call a header file. A header file. The intention of a header file is it can be shared by multiple source files. Okay, but in this case we only have one source file, so it's not going to be shared. But I still want you to get used to the concept of using a header file. So this is the only one, and we'll go ahead and take a look at main.cpp or main.cpp. So we'll do a pound include in double quotes. Okay, this one has to be double quotes. If it is your header file, you use double quotes. If it's a system header file, you use the angle square brackets. And angle brackets, not square brackets. Okay, so in this case, it's just fraction.h, just like your program. Yep.
So the only point of that is basically so we don't have to type out all those 6 lines or whatever at the
That is
beginning.
correct.
So that's all it does. It's just.
That's all it does. But in this case, since we have a really simple program, it doesn't seem to have any payoff. But in a much more complex program, you will have like 20 source files that need the same definition. So instead of copying and pasting the struct definition in all 20 files, which is problematic because if you change the definition, now how do you make sure all 20 files are all updated? So this is a way to make sure that when you're handling a large project, one change to one file will fix all of the source files. Yep.
Can you repeat the purpose of fraction.h here?
Okay, fraction.h is what we call a header file, and it's okay. The mechanism of pound include is just what the directive suggests. All it's going to do is to say, I'm going to go to fraction.h in the same folder because it's using double quotes. It's going to go to the same folder and locate the file fraction.h, which is just a regular text file. It will bring in the content from fraction.h so that it is as if the content of fraction.h is as a part of main.cpp. Okay, and the main purpose is for small projects like this one, it doesn't seem to make a lot of sense. But when you have a large project, you might have 20 out of 50 files that need the same definition. So that makes sense because now instead of copying and pasting the definition of a struct fraction 20 times, you only have to handle one file and have 20 pound includes in the source files. So when you change the header file, all 20 files that depend on the structure definition they will all get updated automatically.
So what you just wrote before, that was the fraction.h, right?
That is correct.
Oh, okay.
Yep. So the file that I just created is fraction.h. So now we can actually go here. And so what I'll do is I'm going to give you a subroutine that illustrates at least one concept that you have to understand, which is initializing a fraction to 1. Okay? So we'll go ahead and take a look at this one. It will be fraction make, okay, initialize to 1. Okay, there we go. It would use the same type of parameter, which is struct fraction, and the parameter is not a fraction, it is a pointer to a fraction, which means the parameter is an address of a fraction. All right, so what is the easiest way to represent the quantity 1 as a fraction? 1 over 1. All right, very good. Okay, I was hoping for something like 73 divided by 73 or something like that. Something that would still be representing 1, but completely unnecessarily complex. Okay, so how do we get it to 1 over 1? Okay, so we start with the only thing that we're given, right? The only thing that we are given is PF, the parameter. What is PF?
Pointer to an address.
It's a pointer to a structure. Okay, it's a pointer to a structure. Okay, so if you start with PF, what is the only thing you can do with a pointer, at least at this point of this class? Okay, well, unfortunately I closed the video already. Oh no, I did not. Okay, so that's good. I just turned it from full screen to not full screen. So when you look at this code, when you look at scan date, what is the one thing that we do to parameter D, which is a pointer to a struct date?
All different parts of the structure.
Not yet, not yet. Okay, if you look at the way we use D as a parameter, what is the one thing that we do with D by itself? The little asterisk symbol, right?
Located?
Hmm?
Located?
Say again?
Located?
Located? Not located, but use it to locate something, right? Because remember, a pointer is instruction to find something, okay? It's a little slip of paper with the address of something, a call number, or just instruction to locate a particular cookie in a particular cookie jar, right? See, I knew that. I knew you guys would remember the cookies, but not the pointers. Okay, so a pointer is an instruction to find something. And the only thing that makes sense is to follow the instruction, right? And the syntax to follow the instruction is a single asterisk symbol. In other words, this one here, this asterisk here, is called a dereference operator. And all it does is to take the instruction in D and say, oh, okay, I'm going to follow this instruction. And in this case, what will you find if you follow the instruction? What kind of thing are you going to find when you follow the instruction? Not a cookie, okay? But what do you find? What is it's a structure, and what type of a structure is it? When you look at the parameter, it says it's a structure type of what? It's a date structure. Okay, DATE with an uppercase D, that's the name of the structure. Is that okay so far or not? Okay. All right. So the only thing you can do is to dereference it. But what you find when you dereference or when you use the address, you find a structure. In this particular program, what you find is a date structure. But in the other program, the program that I am currently writing, what do you find?
Fraction.
You find a fraction. Okay. All right. So let's do it one step at a time. So the only thing we can do with a pointer is to dereference it. At least at this point, that's the only thing we can do to a pointer. When you dereference a pointer, you get whatever it's supposed to point to, right? In this case, it's supposed to point to a struct fraction, a fraction structure. Is that okay so far?
Bracket or the parentheses is the dereference.
It is actually, it's not the parentheses, it's the asterisk symbol. The parentheses is only here to group the operation, because without the parentheses, the dot notation takes precedence, which will kind of break the program. Okay, so when you look at this whole thing, okay, which is the one thing that is pointed to by PF, it is a structure. What can we do with a structure? Sorry? No, a structure has what? What makes a structure a structure? Why is it not the same thing as just a regular integer?
It has members.
It has members. Okay, very good. It has members. So what we can do with a structure is we can say, hey, I don't need the entire structure. I just want one of the members of a structure. What is the syntax to designate a particular member in the structure? A single dot. Okay, that's the apostrophe S, right? Okay, so we can do something like that. So that means, we can now specify which member we want to access. So how do you initialize a fraction to 1? What do you want to store into the numerator? A 1 would be fine. Okay, so you say numerator gets 1. Okay, fine. That's good. What about the denominator? We want to store a 1. Okay, so let's go ahead and do this again. Okay. We start with we start with the one thing that is given to us, which is the parameter, which is PF. PF is a pointer to a structure, and at this point of this class, we can only do one thing with a pointer, other than passing it to another subroutine. The only one thing we can do is to dereference it. Dereferencing a pointer simply means you are following the instruction to whatever the pointer is pointing to. Okay. So if PF is a little slip of paper of the instruction to get to a particular cookie, now we have a cookie. But this is a pretty big piece of a cookie. It has multiple parts, okay, because it's a structure. And with a structure, the only thing we can do with a structure, at this point anyway, is to designate a particular member. Which part of the structure do we want to access? The denominator. Okay, so we say denominator, and the denominator is nothing more than an unsigned integer. So what can we do with an unsigned integer? We can change the value, we can add, we can subtract, and do all sorts of stuff that you can do with regular integers. So that's what we can do. All right? So are you guys getting a general idea of what you need to do with your homework assignment? Because I think the missing link is just, how do we utilize the parameter to get to parts of a fraction. Once you can get to the parts of a fraction, the rest is really just, we put it into the scanf, or we put it into the printf, or we need to do some calculations with it. Okay. Are there any questions about this? Yep.
So as of right now, it's initialized to 1, right?
That is correct.
So then, if we were to put another function below it, will it store that value of 1 when we poll?
Yeah, absolutely. So what we'll do is we'll test this, right? So we'll go ahead and test this particular subroutine, because one thing you should learn in my class is you don't trust me, okay? Not that I want to intentionally lie or give you, wrong information, but you should always take it with a grain of salt. And does anyone know the origin of that phrase, take it with a grain of salt? What is that salt is supposed to do? It's not for seasoning purposes. It's actually supposed to be the antidote of poison. Antidote of poison. Okay, so the phrase of take something with a grain of salt means you're taking in a small dosage of poison, and you want to take in with the antidote so you don't get poisoned. Look it up. Wikipedia has a page on it.
Did
Okay.
you write it?
Hmm?
Did you write that page?
No, I did not. The good thing about Wikipedia is if I write anything that is not true, somebody will come along and say, no, that's not true, let me rewrite it, right? And then you can look at the history of all the wiki pages and find out, how a particular page has been edited, throughout time. With technical stuff, I have pretty good confidence, with the technical stuff, like anything related to programming, networking, math, physics, and stuff like that. With political stuff, you can actually check the history, and they get changed, multiple times per day, and each time it's like dramatic changes. It's not like, oh, I think natural numbers should start with 0 instead of 1 or something like that. It's like completely different, completely different spiel about a politician. All right, so getting back to this program, we have a struct fraction. I'll call it x here, okay? So what this is doing is it's declaring a local variable called x, much like int x, okay, with all of our other programs. Except in this time, x is not a quote-unquote simple variable. It is now a more complex variable, which is a structure. But the concept is still the same, okay? X is still a local variable. It's just that it has multiple components or multiple members in this case, because it's a structure. So what we'll do is we'll go ahead and call the subroutine. Now because fraction initialized to 1 has no return value, I cannot put this invocation into anywhere else, okay? It doesn't really go anywhere except all by itself. When I call this function, I cannot just specify x, because x is a structure, but what the parameter is expecting is not a structure. It is a pointer to a structure. Is that okay so far? In other words, people are asking you, where am I going to find a cookie? You're not supposed to give a cookie to that person, but the location, where do you find a cookie? Okay? Are you guys getting this part? So let's say you're eating a really delicious looking cookie in the parking lot. Okay? And somebody walked by and say, oh, that looks really good. Where did you get it? Okay? So what would be your answer? Here, you can have it. Okay? That doesn't work, right? You have to tell the person where you got that cookie. So you're supposed to give the address of the structure, not the structure to the subroutine. Is that okay? And I can already see next Monday, people remember the parking lot, the cookie, but not quite why we are supposed to pass the address and not the cookie, the structure itself. He was asking first, and then back to you. Yep.
Okay, so with x, we're giving the direction to the cookie?
X is a cookie. X is a piece of cookie. Okay, so if you do it the way it is right now on line 13, you are basically giving that person who asked you where did you get that cookie, you're just saying, oh, okay, you can have mine. Okay, which is not what the other person is asking for. Now, when you use the ampersand, okay, let me answer your question then. Go ahead.
So the fraction initialized to 1 is saying, we're saying that this is a fraction structure.
This is the address of 1.
Okay.
In other words, you are given the GPS location of the store that sells a particular kind of cookie. But you're not given a cookie at all. Is that okay? No? Okay, so I don't have any actual, well, actually I do. Not cookies, but I have Aussie Bites. Okay, so we'll just pretend, since I'm not supposed to eat in the class. So, okay, so this is actually perfect. Okay, this is a structure. Man, I just got all kinds of props in my bag. So this is a structure because it has 3 members. Okay, we have 3 Aussie Bites here, 1, 2, and 3, right? So this is a structure, it simply has components, and you can specify which component you want to access, okay, by name. All right, so let's say I'm holding this bag in the parking lot, and and I was about to eat it, okay? And somebody passed by and say, hey, that looks really good, where did you get it? So what is that person expecting? Is that person expecting me to hand over my Aussie Bites? Or is that person expecting me to tell that person, oh, I got it from Costco, or a particular Costco in this case? Okay, that person is expecting me to say, oh, I got this from the Costco on Auburn Boulevard. Okay, that's the same kind of stuff that's happening here. The subroutine fraction initialized to 1 is asking for an address of a structure. It's not asking for a structure, it's asking, where do I find a structure? That's what the asterisk is. Okay, it is asking for an address. So if I give it just X here, it is equivalent of handing over my bag of Aussie byte and say, hey, you can have mine. That's not what the other person is asking. Yep.
So the asterisk is the location?
Sorry?
So the asterisk is the location?
No, the asterisk is saying it is a pointer to a location. Okay? So there's the asterisk and there's the ampersand. They are kind of opposite to each other. So when you use ampersand on one side and then you use asterisk on the other side, they quote unquote cancel out. One is taking the address of. In other words, one is saying, oh, okay, I like these Aussie bytes, where did you get it? Okay, that is the ampersand. So when the other person at the parking lot, after I said, oh, I got it from the Costco on Auburn, okay? When that person used that instruction and drive to Costco, that's the asterisk operator to follow the instruction to get to it. Yep.
So the physical address is the ampersand, and the instruction to get there is the asterisk?
Yes, that is correct. So when you define a parameter, it has to use this format here because PF is a pointer to a fraction structure. That's how it is denoted using C and C++. We okay with this? Okay. So if it is okay with this, then we know for sure that line 13 has a problem because it is passing the structure itself, not an address of the structure, which is not right. Okay, the compiler will complain about this. So we have to use ampersand and say, oh, okay, by the way, I'm not giving you the cookie or the Aussie bytes, I'm giving you the address, okay, where I got it. Okay, the ampersand is where did you get it? What is the address of? Okay? And that's the entire program. This is all I'm going to do, and we'll go ahead and check it out, see if it works or not. Now, we will check it in GDB, and in this case, this session of GDB is also helpful for those of you who are kind of more visual and kind of need to look at something to get a really good grip on the concept, because in this case, GDB will be quite useful for that purpose. So we'll do a warn all and -c main.cpp. GDB main, and we'll put a breakpoint on the main subroutine. Okay, run the program. Now we are ready to call the subroutine. So first thing is to take a look at X before we go in, just to see what it is and what the compiler can tell me about it. So it tells me that X has two components, has two members. The first member is numerator, it has some gibberish value, and then the denominator has a value of 0. But that's okay, because this is uninitialized. Okay, anything that is uninitialized can have any value whatsoever. Okay, so this is perfectly okay. This is normal. But I want to also tell you what is the address of X, because GDB understands C syntax, which is really nice. Okay, so now it's telling me that the address of this particular fraction is at memory location BFFF F9B0, which is a pretty big number. Okay, if you convert that hexadecimal number, base 16 number, into base 10, it's a pretty huge number. But that's okay, because even though this seems like to be a huge number, how many bits do you think it is using to store that particular address? One hexadecimal digit takes 4 bits. So how many hexadecimal digits are we dealing with here? The 0x part is just a prefix, so the actual digit, the first digit, is B. How many digits are there? There are 8 digits, okay? There are 8 hexadecimal digits. Each hexadecimal digit takes 4 bits. So how many bits do we need to store this number? 32, right? So how many people are still running a 32-bit operating system on your computer? Few, okay? And that's because with a 32-bit operating system, you can only address up to 4 gigabytes. And how many people have a computer with more than 4 gigs of RAM? Most of you, right? So that means this is not even a big number, okay? We can't even get past a 32-bit address system using 32 bits. That seems cyclic, right? But it's not a big number. It's not a huge number by comparison. It's just a number. It is the address of something. Are we doing okay so far with this? This is where I got my cookie, or Aussie Bytes. Okay? It really is the address. This is literally the GPS location of that bag of cookies. Yep.
So how does it know where X is? Because you said that the ampersand X in the program, but there's no X in the structure function, I guess.
But we are not in the structure. We are not in fraction initialized to 1. We are still in main at this point.
Oh, okay.
Yeah, we are about to call the subroutine, but we are not quite there yet.
Okay.
Okay, that's a good question, but it has to do with we are still in main. Yep.
What will it print if you do like print asterisk X?
Say again?
If we do print asterisk X, what will
It will complain and say we cannot do that.
we cannot?
Because X is not an address, and you cannot follow. Okay, see, you can only follow an address or follow the instruction to drive to a location. So if I give you a sheet of paper with all the turns and where to go, which street to make a left turn or right turn, you can follow that instruction, right? The asterisk operator is following the instruction to go to some place. On the other hand, if I give you a piece of cookie, can you use that as instruction? No. X is a piece of cookie. It's not instruction to go somewhere. Okay? All right? Shall we proceed? So now we're going to single step. Okay? I'm going to use a single step to go into the subroutine. Now, this is important. When we get into the subroutine, the first thing GDB tells us is PF is BFFF9B0. It's the address of the structure that we're dealing with. So PF itself is not a structure, it is a pointer to a structure. It stores the address of a structure. Is that okay? Okay, now that we are in the subroutine, X is no longer visible. So if I try to say print X, X is not accessible because it is a local variable that belongs to main. I can ask what is PF, and it says PF is an address of a fraction, because that's basically how you read it. So instead of saying it's a fraction, it says this number is a pointer to a fraction. That's basically what it's saying. Wait, if this is an address, I can apply the asterisk operator because it is telling me where to find something, so I can actually follow the instruction and say, oh, I'm following the instruction, tell me what is at that location. So we can certainly do that. And is that looking familiar? So even though the subroutine does not have access to X as a local variable, when you give it the address of the local variable, now the subroutine has a way to get to it using a pointer. Is that part okay? Okay. If this is okay, then I can do something about the first statement. I'm just about to execute the first statement here. Okay, this is the statement that I'm going to single step into. All right. All right, so after this, I'm going to print whatever PF points to, and you can see the numerator is now updated to a 1. Now, if I were to print PF all by itself, do you think that is changed in any way at this point? The pointer itself is not changed, but what it points to is. Okay. But just for confirmation, let's double check. PF is still the same thing, right? It's still BFFF9B0. So we are not changing the pointer, we are changing a part of what the pointer points to. Is that okay so far? Okay, we'll single step the second instruction, which is putting a 1 into the denominator, and then we'll do the same thing again, asterisk PF, and it tells me both are now 1s. And the GDB also understands C syntax enough that you can actually just say, okay, What PF points to is a structure, so I follow the instruction to get to a structure. But I'm not interested in the entire structure. I just want a member of the structure. Now we can specify, just one of the members of a structure. Press the Enter key, and this time it only prints one of the members instead of the entire structure. So just about anything you can do in the C++ program, you can do it in GDB as well, which is really nice because this really helps when you are debugging your program. You can examine, what is the parameter, what it's pointing to, what is the value of each particular member, and you can even change those things, in GDB when you're debugging your program. Are we doing okay so far with this? Sort of, more or less, kind of fuzzy. C++ and C are the only two quote-unquote popular programming languages that has the concept of a pointer. Okay, Java doesn't have a pointer. Visual Basic does not have pointers. Perl does not have pointers. PHP has no pointers. Python has no pointers. And this is the only programming language that has the concept of a pointer. But it is a very useful concept. Yep.
So instead of being able to pass by address, they just have to return a value to change the variable in the function.
They have a different way of doing things. They can, instead of pointers, they have what we call references, which is not exactly like a pointer. Things are kind of more hidden, and they do a lot of automatic stuff in the in the background. C is very explicit. Okay, you're dealing with very low-level constructs, even though it's supposed to be a high-level programming language. Are there any questions about this program? I'm going to get out of GDB right now and just kind of document the program a little bit, just so that you guys have a way to refer to these concepts when you're doing your homework. Okay, so this is basically saying follow the pointer and find out what it points to. Okay. Is get a particular member of the structure pointed to by PF. Okay, I know the the description is not really exactly super helpful, but spelling it out definitely should help a little. And then with this line here, I'm going to just comment it here and say, take the address of X and pass it as an argument to function fraction initialize to 1. Okay. So I'm hoping this helps up a little bit, by documenting the program in the context. Because otherwise, I can describe, what the asterisk operator is, the ampersand operator, all day long on a piece of paper, and it's not going to help. With this one, I'm hoping that it's helping a little bit. Yep.
So that last line, is that why when you printed ampersand X and then the asterisk PF, they're the same thing?
Yes. Because they basically undo each other. Right? Are there any questions about this? Maybe it helps a little bit if I just kind of give you a general concept of how things are organized in memory. Okay. So let's say this is the computer's memory. Okay. And obviously, it's not going to be to scale. Okay. The computer's memory is organized in bytes. Okay. The i386 processor architecture, which is used by i5, i7, and all the variants of that processor today, is what we call byte addressable. Now, byte addressable means that every single byte, okay, which is 8 bits, in the computer has its own address. So naturally, you have the first byte of the entire memory system, and then you have the last byte of the entire memory system. Now, whether this is virtual memory or whatnot is not important. Okay, so in this class, I'm not even going to get into that part. but it really helps to understand that this whole space is just ordered from 0 all the way up to the last number. In a 32-bit system, it's just going to be FFFF, FFFF, which is basically all ones, 32 ones. So this byte has the location of 00000000 in hexadecimal because we need 32 bits. This byte here has the address of FFFF, FFFF, which is also in hexadecimal. Okay? Are we doing okay so far? This is your entire memory space, which is equivalent to all positions on Earth. Okay? But do you find a factory, a shopping mall at every single location on Earth? No, there's a lot of in the middle of nowhere, right? Okay, and it's the same thing with the memory space. Your program, your variables and whatnot occupies a very tiny portion of the entire memory space. Is that okay? So when you look at the area of the Arden Fair Mall, okay, how does that compare to the entire surface area of the Earth? Tiny, right? Same thing with your variables. So your variables are really using up very little space in this entire memory space. But the most important part is it is still here. In other words, it has an address. Are we doing okay so far with this concept? Everything that you do in a program, your variables, everything has an address. Now the cookie cutter is an exception to the rule, okay? Because you're only using it to cut out cookies. Anything like that does not use up memory. But in this case, variable x, which is a fraction, does take up memory space. So this is our local variable x. It takes up some memory space in the memory. It takes up multiple bytes, okay? Because if each component is taking up 4 bytes and we have 2 components, it's going to use up 8 bytes, right? So it's going to use up 8 bytes here, but it doesn't matter. It has to start somewhere. Is that making any sense? That somewhere is $x. That is the address. The content refers to what is in these 8 bytes. The address is from 000000000 to FFFF. Where is the starting point of this thing? Is that picture helping a little bit? More or less? Okay. And this is actually how things are kind of organized in memory too. Yep.
So when we point to that x, we're getting out of a point. Is that, I know it's just, you said it's just calling slip. Is it giving us the value of x?
Which one?
A pointer.
A pointer? Okay, so $x is on line 17, okay? But when you pass $x to the parameter pf will point to the same place. In other words, pf in the subroutine is basically indicating the same address. But pf by itself is nothing more than the address of a byte in memory. You cannot really do much with it. But when you dereference pf, then you're getting to these 8 bytes. So these 8 bytes, when you look at this chunk of memory, that is the dereference version of pf. But the dereference version of pf is including all 8 bytes, okay, both members of the structure. If you want to access only one of the 2, then you have to use the dot notation to specify, oh, I want the first one, or I want the second one. So the dot notation allows you to access a particular member in the structure. The asterisk operator allows you to follow a pointer to the memory or the location, the content at that address. Are there any questions about this?
So is that a reason why you said if we put like Mr. X with X, it's not going to give us anything because
it's not only give you nothing, the compiler will complain because you cannot dereference a structure. You can only dereference a pointer. Next time you send a letter to someone, instead of writing down the address, you use duct tape and tape a cookie on it and see what happens.
Yeah.
That's what happens when you say asterisk x. You're pasting, you're basically, instead of writing an address on an envelope, which is a way to get to a certain place, okay, you're basically you're hard gluing a piece of cookie on the envelope and put it into the mailbox. The mailman would probably say, "Thank you," you know. Oh, yeah, hot glue, not good. But that's that's the analogy, okay? Yeah. Are there any other questions? So I'm not really sure whether the analogy is helping or hurting, because most people tend to remember the distracting part of the analogies and not really the essence of the concept. Yep.
How do we know that each member takes up like 4 bytes? Like, what is that?
Because it's 32-bit wide. Because when we, okay, let's go back to fraction.h. So when we go back to fraction.h, the type of numerator is uint32_t, and that tells you it is, u means it's unsigned, which means you cannot store negative values. It's an integer, int. 32 means it's using up 32 bits. And if it's using up 32 bits and there are 8 bits to 1 byte, that means each member is going to take up 4 bytes. And together they will take up 8 bytes. All right. Good questions. Any other questions? No other questions? So do you guys feel ready to take on the homework assignment? No? Which part?
The second. The second one, the second main lesson.
Second part?
Yeah.
Which part? You mean this part here, where your code is supposed to go? Okay. Well, okay. Let me ask you this question then. How many people feel confident they can get fraction scan done, which is a combination of scan date from the previous sample program that we talked about on Monday, as well as read num from the previous homework assignment, which we talked about already as well. So that part is okay, right? It's a combination of those two. Print is easier. Okay, printing a particular fraction is a whole lot easier because it doesn't involve any logic. You just use printf, and you just have to pass the right parameter to printf and the right format string, and it's done. It's a one-liner, literally a one-liner. So the most complex one is just simplify. But if you already know how to get to the numerator of a fraction, and you already know how to get to the denominator of a fraction, it really is just boiling down to the actual logic of factoring a number. Haven't we done something with factoring already? Okay, so you can use about the same logic as that. Okay, so what do you guys know what to do with simplifying a fraction? How would you do it? If I give you something like we'll make it easy, okay? So how would you do that? Now, we can use the eyeball algorithm and spot right away, hey, 5, right? But if you don't do that, if you do it systematically, how would you do this? How would you try to simplify this particular fraction? Just, yeah, go ahead.
You'd have to use find factor for both. And
Yep.
somehow find a mat.
You can either apply find factor for both numbers, like do it to the first one and then do it to the second one, but they may not agree, right? The first prime factor of the first number may not agree with the first prime factor of the second number. Even though they do share one, they may not agree. Is that okay? So what you, yep, go ahead.
We have to find all the factors. We have to find all the prime factors for the top and the bottom.
In a way, yep, go ahead.
You can mod the two numbers until it reaches 0.
But they may not be moddable anyway.
You can take the remainder, plug it into a new variable, and mod that until it reaches 0.
Okay, so I think you got the right idea. Okay, it's just the way you describe it. It's,
okay.
Yeah, that's okay. I think you got it though. Okay, so what you do is you say, oh, let's take a look at the first number and mod it with 2. Okay, 2 is not a factor, right? So I don't even need to bother with the second number. Okay, if 2 is not a factor of the first one, I'm not interested in it. Is that making any sense? So you keep testing it until you get to 5. Then you go like, oh, okay, the first number is a multiple of 5. Maybe the second number is also a multiple of 5. It may not, okay? You've got to keep that in mind, is the second number may not be a factor of 5. So now you take this 5 and go like, let's check the second number and see if the second number is also a multiple of 5. If you discover that it is also a multiple of 5, the second number, then you have just found a common factor between those two. Then you can divide the numerator and the denominator by 5, and then repeat the process. Now when you repeat the process, you don't need to start with 2 anymore, because you already tried, right? So what do you start with? Not 6, try 5 again. Does that make any sense? You don't want to skip, and say, oh, we tried 5 already, let's move on. Because what if I give you this instead? If I give you 625 and let's say 100 here, okay? Then 5 appeared more than once in both numbers. So you got to try 5 and then try it again. Keep trying until it fails. Because the first time you try 5, it will identify 5 is a factor of both numbers. But what happens when you have 625 divided by 5? You get 125, and 100 divided by 5 is 20, right? 125 and 20 get both multiples of 5. So you have to try 5 again. You can restart from 2, okay? It's not wrong to start from 2 again. It's just extra time cycles that you'll be wasting, which is okay. Okay, for this homework assignment, it's not. I'm not going to grade based on the efficiency of the algorithm. You can start with 2 again. I'm just saying that if you already identified 5 is a factor, you can just try 5 again and again until it is no longer a factor. You keep dividing the number. Yep.
So how do you retrieve actually the value that you wanted? Because you wanted like the value that
I wanted to simplify all the way, right?
Yeah.
So 125 over 20 is now simplified. If you divide both the numerator and the denominator by 5, then you get 25 divided by 4, and at that point you stop because they cannot share any common factors anymore. Okay. So you have to find out, how do I know this number can no longer be simplified any further?
And that also like using just the mod function, because the mod function is only going to give us if there's a reminder, it's going to give us the reminder. If there's no reminder, then it's just a 0. So how are we going to retrieve the 125 to actually?
Well, there's no such thing that there's no remainder. There's a remainder of 0, right?
Yeah.
Okay, so it always gives you the remainder of a division. It's just that sometimes the remainder of the division is 0.
Yeah, that's right.
So if I give you 25 over 4, how do you systematically, find out that, hey, this number cannot be simplified any further? Well, you try 2, right? Okay, 2 is not a factor of 25. Move on. 3 is not a factor of 25. 4, 5. Okay, 5 is a factor of 25. Good. Then you say, oh, is 5 also a factor of 4? No. Okay. But you can actually exit right now because 5 is already greater than 4. There's no chance I can find any common factor anymore at this point. Okay. But you can keep going until you go to 25 and then you can exit, right? Yep, go ahead.
So we're just using the modulus operator on the reference value, right?
Yes, you are using the mod operator on the member of a structure that the pointer, which is your parameter, points to. Okay, let's go back to this picture here. Okay, so let's see what you're doing, what you're modding, what you're using for the mod operation. Okay, so I'm going to erase some of this stuff here. Now what I do want to keep. Okay, so you have a struct fraction sitting somewhere in memory, which is this guy here. And it has no name, okay? At this point, it has no name because you have a parameter that is a pointer pointing to it. So it's no longer known as x. It is just something that pf points to. Is that okay? So you have pf, which is your parameter, and it points to the first byte of a fraction. Can you mod a fraction? Can you mod a pointer, first of all? No, well, not really. Can you mod an entire fraction? No, the mod operator is only applicable to integer values. Okay, so what you need to do first is to say, oh, this is a pointer. The only thing we can do with a pointer at this point is what? Dereference. Okay, so you say dereference. Okay. I use extra parentheses to be very clear. When you dereference PF, you get all 8 bytes. I cannot mod with all 8 bytes, okay? It's not an integer, right? But what I can mod with is a particular member of the structure. So I'm gonna say, well, we can pick one or the other one. So I can, let's say I pick the numerator. Now we have an actual integer, and you can use the mod operator on an integer. Is that okay so far? Every time you start with something, you kind of have to think about what can I do with this. Okay, a pointer you can dereference, an integer you can do multiplication, division, mod, and so on and so forth. A structure you can access a particular member, or you can take the address of. Now, taking the address of is actually quite universal. You can take the address of just about anything that can store something. So that means you can even take the address of a pointer. The pointer itself is taking up some space. In other words, PF is actually stored somewhere within the memory system of a computer. So you can take the address of a pointer, and then it becomes a pointer to something. It's just like you're following like a treasure map, okay, or treasure instruction. So the first stop, would be you dig up something, and in that something will be a little scroll of something that tells you where the next thing is, and you go to the next thing, you dig it up, and it's the instruction to find another thing, and that's the same thing, okay? You can have a pointer to a pointer to a pointer to a pointer. It's the same concept. Each one is just the location of something else. Right. Yep.
So if we were to use your example program that you used, pf.numerator would have a value of 1.
You mean this one?
Yeah.
So this one is very simple, okay? It does something that your program does not need to do, but it does show you the syntax to do what you need to do. And the concepts of it shows you what you need to understand to get your homework done. Which is starting with a pointer, you get to a structure, getting to the structure, you get to a member, and once you have the member of a structure pointed to by a pointer, then you can do whatever an integer can do, right? You can store something into an integer, you can do a mod operation, you can compare, you can do all kinds of stuff where just whatever you can do with an integer.
To print on a different function for the print, do you want us to use the how do you want us to print?
I want you to print, like in this case, I want this this particular fraction to print out as 1/1.
Okay.
Okay, so you have to get to the integer again, right? But the subroutine is only given a pointer. How do you get to the integer? So you say, okay, I have a pointer. The only thing that we can do is to dereference it. You dereference a pointer, you get a structure. So what can you do with a structure? One of the things you can do with a structure is to access a particular member. And one of the members, in fact, both members are unsigned integers. And then you just have to find out the right way to do the format string, which I actually mentioned earlier in class already. And that's it. Okay. Any other questions? No questions. No? It's all good? All right. Well, this is due next Wednesday, which means we still have Monday to talk about it. If you guys start to do the homework assignment and you're kind of stuck with a particular concept, we can talk about it on Monday. but it relies on everyone to start early and not wait until 7 a.m. on next Wednesday and go like, I have no idea. All I can remember is Costco and cookies and Aussie Bites. Hello? In the parking lot, exactly. And then all the rest is like a blur. Man, it's making me hungry. I need to go get a cookie.
Office hours. That's what you say, office hours.
Office hours.
7.
Yep, office hour is right before this class, which is extremely convenient, right? And I'm usually in my office by 7:15 or so. So you can, if you're an early person, you can stop by my office before 8 o'clock. Any other questions? Okay, no other questions? All right. So if there are no other questions about the homework assignment, we'll go back to the topic and just kind of finish up, all the stuff, all the notes that I have typed up. We are done with structure. What is a structure? Okay, which is basically a way to contain multiple items. That's basically what it is. And this particular example we used already, okay, is how do we represent a date using the human readable format. Now, since we are on this topic, how do you think a computer represent a date? This is how we like it, right? Because we talk about a particular day using year, month, and day of month. But how do you think a computer represents time in general on a computer?
A single number.
A single number, and it's going to be an integer, okay? So how do you use a single integer to represent time? I think you kind of know the answer, okay? Go ahead. If anyone wants to talk about it. Okay, in Unix time, it is represented by the number of seconds since 1970, January 1st, midnight. Well, that's not enough, okay? Because then it depends on which time zone, right? It's GMT, Greenwich Mean Time. That is the reference point of everything, where everything starts. So today, right now, is just represented as the number of seconds since that particular moment. That's how your computer represents time. Now, why do we want to represent time like that inside the computer? Well, first of all, it makes it very easy to compare. Given 2 time, you just use an integer comparison. That's it. That's all you can. That's all it takes to know which time is before which other time. Okay? Calculation is easy. Okay, what is the time 1 day from right now? You just add the number of seconds in a day, and the sum becomes the same moment, but of the next day. Is that making any sense? You don't have to take leap years into consideration because you're only counting the number of seconds since a moment. So leap years do not apply at all. Is that making sense so far? Okay. So if the computer is keeping track of time like that, how does it reverse it back to the way that we can see it, that we can understand easily? But it's a lot of math. Not a whole lot, but there's some logic, math, and stuff like that. And I think that will make a nice homework assignment as well. I'll give you the number of seconds since that moment, and you tell me what year, what month, what day of month, what hour, what minute, and what second. It's tedious, okay, but it's not really horribly difficult. Okay. So keep that in mind, when you're working on your homework assignment, and kind of think about it a little bit. What is the logic to reverse that? Okay. All right. So that's a little bit of a sidetrack here. Okay. So that part is done. This slide talks about how a structure can be embedded into another structure. So in this case, we have a structure to represent date. This is actually incorrect because a year requires more than 8 bits to represent, so it needs 16 bits actually. In this case, we have a time, which is represented as hour, minute, and second. And if I want to derive a timestamp structure, then it will need to have 2 components, or 2 members. The first member is the date, the second member is the time. This is okay in C++. You can use a structure as the type of a member of another structure. and this can nest, as deeply as your program needs to go. Is that okay? And now the next question is, how do we get to a particular thing? If I give you a timestamp, how do you get to, let's say, the minute of that timestamp? Well, you just need to have 2 dots, right? Something like this. Crash time is a timestamp, and dot time gets to the time member, but the time member itself is a structure time, and with a structure time, you also have a minute member. So you can get to the member of the outermost structure, which is also a structure, and then you can get to the member of the inner structure like that. So the dot notation can deal with nested structure by just chaining all the dot notations. Okay. Are there any questions about nesting structures? No questions about nesting structures? Alrighty. Yeah, this part we haven't talked about. We have not talked about C in and C out, so don't worry about that part. Okay, that is the part that we'll talk about later on. And what we can do with the structure, we can access the individual members. We can do assignments. Okay, we can copy a structure to another structure, which is not something that we have done yet at this point. Okay, we have not had the need to copy a structure. And this is big, okay, as an encapsulation mechanism. So encapsulation is a hyperlink all by itself, because you can actually go to the wiki page of what encapsulation means in object-oriented programming. So I'll just kind of go over this very briefly, because this is a really long document and I don't want to read the entire thing. Encapsulation is the packing of data and functions into a single component. The features of encapsulation are supported using classes in most object-oriented programming languages. C++ is an object-oriented programming language, and you can expect to use classes in the next class. Okay, no pun intended. The next class is cisp360, which is object-oriented programming. In that class, they will extensively talk about the concept of using a class, the concept of a class in object-oriented programming. We are not going to spend much time on it. The only thing I can tell you at this point is structures and classes are very much related. They're very close relatives. Not exactly the same thing, but very close. Okay. Although other alternatives do exist, it allows selective hiding of properties and methods in objects by building an impenetrable wall to protect the code from accidental corruption. This, I will leave it up to the professor of cisp360 to explain. Okay, but one thing I can also I can tell you right now is it has to do with abstraction. Okay, classes, data structures, good programming practice. Most of those things have to do with insulating changes or errors or bugs from the rest of the program. Okay, let me tell you an analogy that will hopefully give you an idea. How many people are old enough to remember CRT televisions? No? Okay, a few. Okay. I'm pretty sure some of you have seen it, okay, even though you may not have seen it at home. Okay, you might have seen it on, older movies and stuff like that. Okay, so CRT is cathode ray tube, and if you look at the images, okay, that's those are all pretty good representative images of CRTs. Okay, the technology behind CRT is they have an electron gun, okay, inside the big tube, which is a vacuum tube. If you think about it, it's really kind of Marvel all by itself. Is you have something about this big, kind of the size of a pretty good size fish tank. If you think about the 30-something inch televisions using CRT technology, that's a pretty big fish tank. And the entire thing is quote-unquote vacuum. It's vacuum in the inside. So you just kind of think about the kind of pressure that it has to deal with, all the force it has to deal with, and not to implode and crack and destroy itself. And that's why they're so heavy, because they need really, really thick glass to withstand all the pressure and not crush it, because you have vacuum in the inside. Okay, but anyway, the technology is it has an electron gun in the inside, which is consisting of a filament heating up something, and then have a charge on one side and a charge on the other side, and the electrons will now want to go from one place to another place, except there's a hole in between, so the electron, instead of landing on the positive plate, it will go through that hole and keep going. So now you have a way to shoot an electron out of the quote-unquote electron gun. Okay. And an electron, being a charged particle, is susceptible to magnetic fields. Okay, so a magnetic field can alter the path of an electron when it's in flight. So now by changing the magnetic field, one is horizontal and the other one is vertical, now you can deflect the path of an electron to go like, I don't want it to go straight, I want you to make a left turn and go up, like that. Okay? And by changing the magnetic field in a systematic way, you can now make the electron gun to scan lines like this. Is that making any sense? Sort of? Okay. Can you see the electrons? Now, we can see photons. We are sensitive to photons, but not electrons. So when the electron hits this quote-unquote screen, it is actually landing on a phosphorus type of material where it will start to fluoresce. Okay, so the electron is giving energy to the fluorescent material, where it will, use the excitation, with the electron and emit actual visible light. And that's how we see images on a CRT. That's the basic technology behind CRT. Okay. What kind of monitors do you guys own at home, or what do you have at home? LCD. Okay, so you have LCD, TVs and screens at home. What is the physics behind that particular technology? LCD stands for liquid crystal display, right? Okay, so how is crystal being used to display something? Nobody knows, or you just don't want to talk about it? Yep. LED is only used for the backlighting, unless you're dealing with OLED, organic LED, which is also used to display directly. But most quote-unquote most of the quote-unquote LED TVs are only using LED as a backlight. Okay, so the way it works is kind of like this. You have light going through in one direction. This is a cross section, by the way, of a TV. So the first thing it would do is it would hit a polarizer. A polarizer will basically block light that is, in a particular axis. Okay, so this will, let's say it blocks the horizontal. It will only let the vertical light go through. And then you have another layer, which is the liquid crystal layer. Now, liquid crystal, as the name implies, is kind of like crystal, but it's suspended in liquid of some kind. Okay. If you don't do anything about it, they're all over the place. Okay, they have different orientations, so they go like all in different directions. But when you apply a charge to these two surfaces, they will start to align. When they align, it becomes a polarizing type of material. So you have one polarizing material here. This one is a controllable polarizing material. Now, when you have polarizing material, if one is polarized this way and only allow light that is going this way, and the other one is polarized in the other way, together they will block basically all light. But when they align, then it's transparent. So this one is fixed. This one you can turn. Okay. If this one you turn and it's like this, then you have light going through, or half the light, sort of half the light going through. But this one is aligned this way, then you have no light going through. That's how they control the intensity of a single pixel. Okay, by changing the bias voltage across the LCD panel. Now the backlight, which is this part here, is not exactly programmable. It's not on a per pixel basis. Okay, they divide it into big blocks, and within each big block, it is somewhat programmable. Okay. Okay, so the two technologies are very different. Okay, when you go home and you turn on your TV and go like, well, the brightness is off. Okay, I need to adjust it. And sometimes, occasionally you need to do that depending on the background light, the room itself and stuff like that. Do you need to go open up the case of your TV, understand all this technology, find out which potentiometer to tweak, and then get a screwdriver and go like, okay, I needed to brighten up a little bit. I think it's this little knob here. Do you need to do that? No. Why not? How do you do it? You get your remote control, right? You get your remote control, get to the OSD, the on-screen display, and you locate brightness, and then use your control thing to change it, right? Okay, and then you go ask your parents, right? Because your parents probably have used a CRT TV before, and you say, see, this is so easy to change the brightness. I bet you cannot do this with a CRT TV. What do you think your parents will tell you? Do you think your parents need to understand the electron gun physics in order to change the brightness of a CRT TV? No. So how do you think they change the brightness of their TV in their generation? Same remote control, right? Same OSD, same on-screen display, and they do it the same way. That is abstraction. Because the abstraction is the losing of details, losing of information that is not important. And in this case, the physics, the engineering behind a television is not important to the consumer. And therefore it is lost, it is abstracted. Now when you abstract something, there will still be something left, right? What is left? After you abstract out the engineering, the physics, and all the components in the background, you get this left. Okay? So now you have a single abstraction that is called brightness control, which is independent to the technology, independent to the manufacturer, independent to the physics. You just go to the contrast control or brightness control, and it works the same way, whether it is a CRT TV, LCD TV, plasma TV, or OLED TV. It's still the same. That is abstraction. How does that relate to this class? What are we talking about? What is the current topic?
Encapsulation.
Encapsulation of structures. Structure would do the same thing to a certain extent. Classes in object-oriented programming extends that a long way, so that from the perspective. Wait, hold on a second here. Who's the consumer here? I'm the developer, so I am both the manufacturer of the television and the consumer of the television. Well, that is true only when you're dealing with your homework assignment. When you work outside, are you going to write a 500,000 line program by yourself? No. You may be contributing 2,000 lines or so. Okay. What about the rest of the program? It's written by somebody else. So from your perspective, you are the consumer of that chunk of code that somebody else has already developed. So the idea is you don't need to know every single detail about the rest of the program. They will be abstracted through structures, classes, and stuff like that. So by the time you have to utilize the rest of the program, you have a clean and simple interface that does not change when the other side decides, hey, you know what, I found a good way, a better way to do something. It would not impact your code whatsoever. That is abstraction in programming. Okay? And structures, I'm kind of running out of time here, but structures allows you to do that. Okay? But with the one example that we have, I can illustrate it already. Only with this simple, tiny little program, I can illustrate the concept of a consumer versus the manufacturer. The manufacturer is the portion that needs to understand how a fraction is represented. That would be the structure definition itself and the subroutine function initialized to 1. What about main? Do you see anything in main that depends on the actual definition of the structure of a fraction? No. As far as main is concerned, it says right here, it says, give me a fraction variable. Okay, x is 1. Does that say anything about the detail of how a fraction is represented? No, it just says, oh, here's a fraction. Okay. What about the initialization of a fraction x here? Do I need to know, oh, that's a denominator, and it's named denominator and not abbreviated to none? Is that here? No. in your program, okay, when you're writing your program, the main function of your program, the program that you're going to write, does it need to know the details of the numerator and the denominator? That they're unsigned, they're 33 bytes, da 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 da. You know, it just says, okay, give me a fraction. The first one says, oh, okay, this is uninitialized. I want to read a fraction from standard input. Call that function. Next, I want to simplify the fraction. Call that function. I want to print a fraction. Call that function. Okay, 3 different functions serving 3 different purposes. But as far as main is concerned, it doesn't need to know how it is implemented. That is abstraction. Okay? So the functions are basically equivalent to buttons on the remote control. It doesn't matter how a fraction is actually implemented. It doesn't matter how the projector, what kind of technology goes into the projector. It's the same thing. If I want to auto adjust, for the width and the height, it's the same button that I press. Doesn't matter. It is DLP. What is the D? Is it digital light processor? Something like that. Doesn't matter whether it's LCD or there are actual tiny little creatures in there with a little flashlight shining on the screen. Doesn't matter. This remote control works in all cases. That is the abstraction. Okay. So that's the whole thing about this particular slide here, about the encapsulation mechanism and how details are hidden from the quote-unquote consumer of particular structures. It's basically, if you don't need to know the details, do not touch the details, because opening up a CRT and tweaking the electronics in a CRT can shock you, because it takes about 4,000 volts in order to shoot electrons out of the electron gun. So if anyone touches the high voltage circuitry of a CRT, that's not going to be a very pleasant experience. If that person survives it. It's the same thing in programming. You don't want to open up something unless you have to. Okay, you want to use the remote control, use the buttons that are given to you as a consumer, and just stay with that. Is that okay? Any questions about all that stuff? It's all mostly concept, but I do have some examples here, so you are more than encouraged to read this part here. It's basically the same thing that I have already talked about, just presented in a different way. So we are running out of time for the lecture. I went over by 10, 12 minutes or so we'll take a 10-minute break, and then when we come back, you guys can start with your homework assignment, and I'll be here to answer any questions that you might have with more questions. Yes?
Do you pass out a motion?
No, I forgot. That's okay.